in person. Thank you everyone for being in person here and also people on Zoom online. Uh, so the topic today I'll be presenting is a modular architecture for scalable and compliant robotics. And this comes from also an industry kind of view with all the edge cases and long-term cases and unstructured environments that we see. Uh, Before I begin, I just want to thank the TILOS AI organization and Dr. Junfei and SDSU for hosting this, and also to Dr. Nikolai for extending the invitation to us. Thank you all. Uh, and Dr. Junfei already gave me an introduction about myself. But yeah, I work at Brain Corporation as a staff autonomy engineer and I lead the perception team there. Uh, yeah, my job is pretty much as you said, to implement real-time perception pipelines using LiDARs, both 3D and 2D LiDARs, RGB, and depth sensors. I can skip because it's already introduced. A little bit about the company I work in. So BrainCorp was founded in 2009, and it's a decent-sized company. We have around 220 plus employees, and a good chunk of it in engineering. We have a great amount of parents in both robotics, AI, visual systems, navigation, etc. We have also a lot of investors, including SoftBank, Qualcomm Ventures, Clearbridge, Hercules, and the Terran Company. And we are headquartered right here in San Diego near Sorrento Valley. So it's quite close to home. It's just maybe 20 minutes from here, give or take. Uh, so what we do in our company within BrainCorp is we have two major product lines, one being the automated floor care and the other being automated inventory management. I'm going to briefly go over these in detail, but in a nutshell, the first one is having robots that automatically clean the floor, maybe a vacuum solution or a scrubber soap solution. And the other is inventory management, where the robot scans your retail store aisles or warehouse aisles, takes images, and then you do inventory management with that. This is one of the slides I'm proud of because we have deployed 40,000 robots worldwide. And within the scanning side, we captured 23 million plus images daily. So having this number of robots is, I believe, a great achievement and also comes with a lot of challenges. Some of them being like we have like in this very unstructured and large environments, including like big box retail stores, airports, convention centers. They operate these robots daily, and there's like people around and other machines around, and we have to make sure that we not only complete a job, we also complete a job safely. And these are some of our customers that we have deployed our robots to. And this is how our robots look like. So the first row that you can see are the scrubber machines, and the small one, there's a vacuum machine there. What they have, this is what I call the Gen 2 or Generation 2 machines. They typically have a 2D LiDAR in the bottom and some depth sensors and a slanted 2D LiDAR. And they do the typical slam, and during autonomy, they follow a pre-trained path. There's also area failure generates path. And all it does is like they rinse and repeat every day, or maybe multiple times a day on airports, and this like have a battery life of 3 to 6 hours, I think. And they are autonomous, completely autonomous. They avoid all obstacles. And the second row here is what we call the Generation 3 or Gen 3 robots. The difference between this is our recent upgrade, and it's upgrade in both hardware and software. We now have 3D sensors. It's completely in 3D. Does a much better job in cleaning like your edge of aisles and walls and stuff like that. And the last three also have the scanning towers over there. You can fit RGB cameras in there, but also RFID sensors like that. You can then sense RFID when you're scanning an aisle. So not only these robots, which we call the clean suite, clean the flows, but they also have complete enterprise tools. So the operator or the store manager can actually see what is being cleaned, what needs cleaning. You can automate, so the robot just powers itself on and does the job, goes back to the dock, and it's a complete end-to-end solution. And in the sense side, we capture images. So you can see an example over there where you have an aisle. We capture images. And once we capture images, we stitch the entire aisle together. And then it goes through our end-to-end computer vision pipeline that does product recognition, barcode matching, planogram compliance, out of stock detection, low stock detection, etc. Or if like a robot is misplaced as corresponding to its barcode, or if the barcode of the promo is expired, stuff like that. And this gets hands-on to the store manager on a mobile app or the uh, the web portal. And apparently, this is very important for them because they do lose a lot of money when things are either like out of stock or not matching their barcode and the other stuff I mentioned. So let's begin with the actual talk about the modular architecture for having scalable and compliant robotics. So before I begin, let's talk about the two extremes in general robotic navigation. And here I mean indoor robotic navigation, which might include path following or following some sort of action where the robot is moving. So on one extreme is what we call traditional robotics. What I mean by traditional robotics is like they are highly engineered systems. They rely heavily on rule-based systems, heuristics, and hard-coded control logic. So it's basically trying to optimize a certain math within a certain complex math. Uh, and it's mostly rule-based. You can't go wrong with that. This is what the traditional robotics mostly has been. The strength within this is like it's very exceptionally reliable and safe, and their boundaries are rigidly defined. We know how the robot's going to behave because of a certain cost function or a certain math is trying to adhere to make sure it doesn't bump into obstacles while following the path. But the bottleneck here is it inherently lacks the adaptability in dynamic and unpredictable environments. I have a few examples when I talk about that, but essentially, like when you take robots, thousands of robots out in these thousand different sites all over the world, you see all sort of edge cases you can possibly imagine. The environments are not only large, they are dynamic, they're unpredictable. Tomorrow they might have a certain problem that was not seen today. So additional robotics may not have all the heuristics to capture all these edge cases. And every time you have, let's say, a new robot or a new feature you want to add to your robot, you again want to write a new software, boilerplate code to just add maybe perhaps simple features. So it's also a little bit difficult to scale these. On the other hand, visual language action models or VLAs for end-to-end autonomy is what sits on the other extreme. So here, VLAs for end-to-end, problem is like right now, these are the hype. The current situation is like the businesses right now and startups are looking to accelerate through just slapping a complete end-to-end model to solve a certain problem, which can be like a simple follow me robot or a robot with arms that's trying to pick and place or fold clothes. But the problem is like it faces an extremely long and expensive road for commercialization, and in my opinion, still does not capture all the edge cases that it can. The other issue is like these models, because they're trying to just take RGB images as input and give just like the complete action as output and everything else being a black box, it's a little bit difficult to train this because you need a lot of data, a lot of training, and the hardware it needs to run these large models is also expensive and heavy, something that robots cannot probably have. We need more on the edge solutions. This is how a typical VLA end-to-end model looks like. So here we have sensor data coming from the left, which can be captured from your sensors like LiDAR, RGB, depth cameras, or they are passed through a visual language model. And then you also have a task, which can be basically a simple motor command to follow the path or to go straight, or even a language input that, hey, follow me or follow a certain path. Both of these, just the images and the command goes to a complete black box VLA, and you get an action to follow a path. While that works, but it's still difficult to scale it across all the dynamic environments. It still lacks a little bit of the application context, and they are difficult to interpret because they're a black box, difficult to debug, and may even lack certain safety guardrails. So this is where we want to head towards, and this is what we also found out at Brain Corp, that hey, we need a solution that sits in the middle, that is not only adaptable but also scalable and has certain deterministic safety. So let me try to give you an example here. But before giving me an example, I'm going to show the contrast of what it looks like. So again, in the left, we have sensor data, which are again capturing images uh, from the sensors or LiDAR scans or whatever, or they may even be passed through a visual language model. And we also have the task coming from up, which can be motor commands. And then we have this BrainOS core architecture, where on the left, you have a contextual grounding layer with semantic mapping. And on the right, we have the context-aware policy. They give a certain action given the semantic map and the policy that it generates based on the task and sensor input. And the output is basically an action. An action can be to turn the wheels of the robot to follow a certain path or complete a task, but they're also bounded by functional safety, where we have a dedicated safety system that runs completely outside this software stack, and its job is to make sure that whenever the robot is executing any actions, it's not touching any obstacles or is not going down a cliff. So coming back to an example, so let's take an example of saying a robot that, hey, there's a spill in the grocery aisle, go clean it. So if this high level task comes to a robot, traditional robotics probably would still struggle to understand where and what is the grocery aisle and what do I have to do. Maybe all it probably can do is like follow a certain path. So you might need a lot more heuristics going on there. End-to-end VLAs, they may have a shot, but they do not understand in the geometric sense where the robot is and where it needs to go, what a grocery aisle is, and how does it like plan, figure out that, hey, maybe like grocery aisle is in aisle 2 or something. Like it doesn't have the geometric information. But within the BrainOS example, you can actually have both a geometric and a semantic understanding of the map you have within the contextual grounding layer. So this is something that we are still exploring, and it's not like a completely solved problem, but we're something that is we are exploring and trying to tackle. But the idea here is you have a geometrically and semantically grounded map that you can query for certain things like grocery aisle, or it has a certain context saying, hey, escalators are a little bit dangerous, don't go close to an escalator. So all this semantic information without having to specifically code, this is grocery, this is aisle 1, aisle 2, aisle 3, this is escalator, without having to specifically code, that encodes in there. And this also becomes like a prior belief for a planner. Now the planner is basically your MPC or some sort of like your motion planning algorithms go here. You can have VLAs as well as part of the simply doing motion planning given the contextual grounding layer and the data and the task. But the idea is to make it a little bit geometrically and semantically grounded and have the motion planner use this information. So when I say, hey, go clean the grocery aisle, the LLM that comes from the task understands what grocery aisle is, gets the vector embedding, let's say, and the vector embedding is also, you can do some sort of similarity or a heat map generation on your map. And then you find out in a geometric space that, hey, grocery aisle is here. I need to go and do an A to B, and I know where my robot is as well in this map. While I go, I'm better make sure I'm not going close to an escalator because you don't want to block an escalator, people are coming out of it. So Let's talk a little bit about the first part I was talking about, the contextual grounding layer with semantic mapping. Before I dive deep, just a quick preliminary information. Uh, so what is basically happening when you use a visual language model or a VLA is on the left, you have an image of a dog, and then you can take the visual encoder, you can take clip or Dino V3, and there are so many VLMs out there. But essentially what they do is they take your image and get a high level semantic embedding. They can also be patch-wise, so they can be height by width by dimension. So the image of dogs get like many patches, and for each patch, you have a d-dimensional vector. The size of the d-dimensional vector and h and w depends on the model you use. But typically, I think for Dino V3, you get like 16 by one patch is 16 by 16. So it's like h divided by 16, the height of the image divided by 16, width of the image divided by 16, and d is a 768 dimensional vector. The 768 dimensional vector encodes the fact that this is a dog. It encodes a vector in this high dimensional 768 space. You can have a vector there. So a vector of a Labrador and a golden doodle might be in the same direction, but vector of a dog and a cat might be in different direction, but they're still in the same sort of direction when you think of animals or pets.
Sorry, Chris.
Yeah.
Are you using language elements here with the output of the VLA, or what's the task here?
So this is just a preliminary thing. I'm just trying to explain how VLMs work and how we can use this technology to get basically a high dimensional map, in this case, a high dimensional 3D map.
Okay, so you're not doing this language alignments with the output of the VLA, or
So we will be doing language alignment of the environment the robot sees when it's making the map. So the map gets this high dimensional language and semantic understanding while still being grounded in geometry. So I have some examples I can show. Let me quickly go through the slide. So you get some patch-wise visual embeddings, and then you also have a textual query like dog. And you're similarly using a clip or talk to Dino V3 or many other textual models, you can get a textual embedding, which is also d-dimensional. And then you can do some sort of similarity, like a cosine similarity, to get a heat map of a dog. So what this is telling that you can obtain or you can get some heat map or some extraction of information given your textual query from an image. So how does this tie with the semantic mapping? So please might answer your question. So this is a very V0 implementation, like a very initial implementation, but this is also where like we want the research to like go towards, and this is just being literally started as we speak. So when the robot is mapping, so what I mean by mapping is the operator is taking the robot and saying like, hey, you have to map a store, or you have to map the environment, and pushes the robot, or it maybe is exploring by itself. And as the robot is mapping, you take a visual language model like CLIP or Dino V3. And as the robot is going, it's not only running SLAM, it's taking the images it captures when it's running SLAM, when it's building the map, and it takes the images. And what you can do is you can project this patch-wise embeddings that you get of the images you capture. So as the robot is capturing and running SLAM, it's taking the image, running through VLM, running a VLM, and it's projecting these embeddings out. So as it's projecting out, it's putting on the map that here that's a whiteboard, here that's a computer, here is a floor, here is a ceiling, but in this high dimensional 768 space. Although this projection logic, I think we believe is like a T0 knife sort of implementation, you can also learn the map parameters here to best align with the embeddings you see in a certain patch of the map. So this is where this paper of learning the map parameters by Kim et al. Is actually the paper as well from the ERL lab by Dr. Nicola here in UCSD. So we do have a collaboration with the lab with Dr. Nicola, and this collaboration is to like figure out like how we achieve this goal. And that's where you also want the industry to like figure out, like move toward that. We need not an end-to-end solution, but something like that is semantically and geometrically grounded. So let's say I am building this map and I have like a 3D pointer of the map or some sort of voxelized representation in 3D of my map, and I put a 768 dimensional vector. It's difficult to visualize a 7-dimensional vector, but I can use PCA to combine it to just one single dimension, the first principal component in this case. So here, what we're seeing is you have a typical 3D map where each pixel is like a voxel in 3D. This is a big box retail store, and you can see some sort of structure there with aisles and a typical large bird's eye view of a map. And the color here is when I talk about a 768 high dimensional vectors for each pixel, I do a PCA here and get the first principal component. So what it figures out is that perhaps like the bottom part is the floor and the top part is the ceiling or the edge of the shelf, and the yellow part is maybe the shell. So again, it's hard to say if exactly this, because we are like trying to see only compress this 768 dimensional into one single component. I'm using Dynamo V3 in this case. Yeah.
So I think you hit some point the search of memory. So if you want to map the environment, the voxel representation, and because your environment is very big, then to map everything in details and high resolution, just like it couple of gigabytes a game needs.
Right.
Or that. So what's your thoughts about that? So how are you gonna make it more to
Yes.
actually store this?
So that's a very good question, and that exactly is the current problem we're trying to solve. What we're doing right now is, so there are multiple ways to solve this. What we observed is like we don't need to save embeddings in a very small voxel grid. The voxel grid size here is 50 centimeters, because maybe a small voxel grid might just have something like this, which doesn't tell much. But having a 50 centimeter voxel grid kind of encodes most of your dynamic big space information. That's one. Two is you might see a certain patch from different angles and you might get multiple embeddings, but we can just maintain one embedding. You can either learn this one embedding by looking at the different embeddings, you just take a simple average. Here we're taking a simple average, but I believe taking a simple average of the embeddings is like you're modeling the bearings that probably loses the fine-grained information it's trying to learn. What Dr. Nicolai's paper does is they learn these parameters, but they learn in a very small dimension. So instead of 760, yeah, it's a latent space. So they try to just like use, I think their latent dimension 64 or 128. But that drastically reduces your size.
Is this the same thing that actually worked on the manipulator, right? The application.
Correct. Yeah. Seeing the bigger picture is a bit. But you're right. They use this to do manipulation. Basically, idea is they tell the manipulator to hey pick up the cup, but it needs to figure out that hey I need to move here to the kitchen where the cup will be. Manipulators right now are just like looking at the table and have like an arm or something and trying to learn episodes, but doesn't generally have this entire scene information, which is also sort of what we're talking about here. I try to also look at the fifth component here to see what's happening. It's a little bit difficult to figure out like what's happening, but maybe the yellow part over there, when I try to look at the map, like, hey, what's happening over there? It seemed like that might be the home goods or trying to perhaps get more similarity on the home goods kind of thing. But again, I think it's a little bit difficult to tell in the PCA world like what's really happening here. However, what we can do is, yeah.
So what is so each of the color represents one category? What's the meaning for the color?
Oh, it's basically like your high dimensional vector is just moved to one dimension. It's hard to tell, but it's trying to see what your most variance is. So, or your most alignment is on your first component. It's like it's
right. So basic PCA is you have some high dimension data, and then you are trying to do some classification.
Correct.
Things, right? You say about the first and the fifth component. Then I'm trying to understand what's the meaning for the color.
Oh, so I don't think like the colors necessarily means because it's like just trying to get one component. So it's hard to say what the colors are representing. But I guess what in a way we can see is like the yellow colors throughout the map, they may be similar stuff that is trying to figure out. And the red is something similar and the blue is something similar. Yeah. Obviously, we don't want to work in this PCA. That was just for visualization. But if we use a textual encoder, I was talking about earlier, if you use a textual encoder and then say checkout area and get the textual embedding of the word checkout area, then you can do something similar like something simple like a cosine similarity, where you can now get a heat map of whatever query you put. So in this case, we put checkout, we just use cosine similarity, and that red thing, which has similarity of more than 0.8, 0.9, that area lights up. When I look at the actual data and try to figure out what that means, is this checkout area over here. So you can basically try, now this is something we did not make the map saying this is checkout area, this is grocery aisle, or this is terminal, whatever in an airport. It has automatically learned or automatically estimated just using a VLM that is trained on whatever it was trained on. So we are not doing a lot of learning here at this point. We can learn the map here, but again, the VLM part is still off the shelf. This is just a contrast of how the real world 3D point cloud look like. Ignore the colors on the floor. They are like zones that we draw for the robot. But just look at the 3D point cloud in gray. You have this gigantic store with all these gray colors. You cannot tell which aisle is what. If you're trying to localize here, we just 3D point cloud, but aisle in the 3D space look very similar. It's a little bit difficult because all the aisles kind of look the same. But when you have more high-level semantic information, your aisles start to look different. Another application is we can do automatic map annotation. Okay, look at the map. If you open up Google Maps, you look at the map, but you don't see text, you'll probably be a little bit confused, like what's happening. What we can do is also do some sort of automatic map annotation, where I take a dictionary of all possible keywords that are applicable on retail or any outer environment. And then I start to basically do the same thing, cosine similarity on my same embedding map, and try to get this text. Or it's a little bit difficult to see, but I'll try to show. So here we see like the frozen section is over here, and I look at the image that was captured by the image you see from the frozen section. Similar, this is the pharmacy over here. We have clothing and bedroom over here, alcohol up there, kitchenware, pantry, breakfast, dairy, meat, and seafood. So kind of is like you're automatically labeling your map in this case without necessarily having to like look and have this very perfect words and you're manually doing it or having some sort of model that you're training to do that. Another application in this is what also we are trying to do is localization in the semantic map. So this is on the left is what we do, which I talked about previously during mapping. You take, when you're doing SLAM and building your map, you also take the images and then you do VLM embedding map. So let's say the map is built and you have this high dimensional semantic map. What you can do is you want to try to localize in this big, gigantic store with exactly similar looking 3D point cloud aisles. But now when they have semantic information, all you do is like, okay, you take your image, when you're trying to localize, you take your image, run the same VLM, get an embedding vector, and then you do cosine similarity on your map, but you also run a particle filter. So you have, let's say, 5,000 particles that are running. It's a lot of particles, yes, but doing cosine similarity is very straightforward. It's a numpy dot. And then you have this, let's say 5,000 or 10,000 particles all across your store. You get cosine similarities, you get the confidences, and then you rinse and repeat. You take the next observation. And then over time, as the robot moves, the particles will converge to what it sees. And this is completely RGB only. This can be heavily and easily augmented with ladder scan matching and all the extra stuff. But here, cosine similarity is much more faster, although you're doing with many particles, but much more faster, where traditional scan matching like 3D ICP is an iterative process. It does take time. So we have some results, preliminary results. So on this large site, what we have seen is if we tell the robot, like just randomly turn off the robot and turn on the robot anywhere in the aisle, if anywhere in the entire store, and we move the robot from 1 meters to 5 meters, the robot can globally localize in the entire map that it ran the whole particle filter algorithm. And this is completely just RGB. And when I say localize, it means, so the metrics are, we move the robot 1 to 5 meters, and it globally localizes from this gigantic, let's say, 50 to 100 meter map to a 5 meter localization, and that accuracy is 90%. If we do 2 meters, the accuracy is somewhere around 75 to 80%. And once we have some sort of a coarse estimate that, hey, you are within this 5 meter, then we can use LiDAR. Okay, then maybe you are in this aisle or between these two aisles, or maybe in this area. Then you can do a LiDAR course to find localization step further to increase accuracy to a centimeter level, which means like you can essentially localize your robot anywhere in a gigantic map. It's localizing in a gigantic map is a very big challenge. And if you are familiar with SLAM, the same cosine similarity and getting the confidence can also be used in your loop closures where you're building the map in the first place. Something to explore we haven't explored yet, but I think it's a great direction. Maybe you get much better and cleaner maps by just doing this. Maybe you can take the Kitty dataset or something to do that. So let's see it in action. Okay, let's see if you guys can see the red particles here. So this is, I'm zooming this area over here, but its particles are in this entire gigantic map. The blue arrow is the ground truth. So we also making ground truth, but algorithm doesn't know ground truth post at all. It's just for visualization. And then we can see that the green arrow, which is the particle filter running, it converges, it moves by almost like, I think it's 5 meter perhaps. And you can see the particles converging here from the gigantic map over here. There, one more example. I think it takes a lot to figure out, but it's pretty much the same thing over there.
I have a question.
Yeah.
So why are you using one gigantic map instead of using backup submaps? When you're looking in submap, we do the localization. But then when you're doing the initial SLAM, you're just making the submaps, but you're also doing some global localization to align the submaps to basically build the overall map. Then when you want to use your model to localize, you can start now your submap action.
Yeah.
So
yeah, that's a great idea. I think if you want to make this reality, there is something we probably will have to do, like work on a submap level, so we can push that accuracy from 90%. But I'm trying to show here like a worst case scenario that, hey, you're not gonna get any submaps. You have to look at a gigantic map and figure out. But in reality, yes, you're right. We will probably look at a more like final level or like a hierarchical submap, some sort of a thing where it's not trying the whole thing, but trying to make a submap.
It's talking about 95% accuracy of what it means. A failure every 15 minutes. So it's not really acceptable for robotics.
Correct. Yeah. I think I also should probably tell like we do have like a complete LiDAR only localization system. It's using and that LiDAR only localization system is responsible for a centimeter level localization and a few degrees of rotation, and that runs your normal autonomy. But to get this in the first place, where you need to begin with centimeter level, we don't have a way. So you might have a designation of a home area or a QR or a code for you to start, but then you're adding a constraint. Someone else had a question here?
Oh, I'm saying, so basically it works well for a static mapping that
Yeah.
the environment is the same, right?
Correct.
Modify a little bit, need to rescan it.
Yes, that's a great question. So another challenge we have to do is to keep the map updated. So that's also a venue we will have to do. And the map updation part is, I feel like, not necessary just for the embedding map, even a 3D map as well. Ice is gonna move, or things are gonna move. You still need some sort of updation mechanism. A very V0 quick implementation can be you just replace the embeddings, but that's like you're losing context from how maybe if you want to track how things are moving. uh, but also, like, one example I forgot to talk about is like when you're looking at this map, you're training this map, there's going to be people around, there's going to be cards around, there's going to be dynamic objects around, which you don't want to store in your map because they might not be present at the same location tomorrow. But in the 3D point cloud, you can not, but maybe you can get, okay, yeah, these are the heat maps of the people and things. With high confidence, I can remove them and maybe have this updation step as well over time running. But that's also an area of research that we should go. I think we only have 20 minutes. So maybe I will have to go a little speed. So, okay, I talked about the map in the whole map. But what about, okay, the robot is now in autonomy and is looking at the current small local perception map. So we also have this in our entire stack. So we do complete sensor fusion of the 3D perception map with 3D and 2D LiDARs, depth cameras, and RGB cameras. And we also run object detection and segmentation models on the edge, on the robot. And their job is to detect humans, escalators, forklifts, etc. We also are looking into litter vision, where the idea is you want the robot to maybe perhaps gobble up or vacuum certain bits and pieces of rubbish, but not gobble up wires because you might pull something, or not gobble up something like a metal object which doesn't deform inside its vacuum packet and even damage the machine. So that segmentation is also handled where it selectively knows which to vacuum and what not to. This is just a very bird's eye view map. So let me quickly talk about what's happening here. So this is the 3D LiDAR depth image where it's like a dome LiDAR. It looks at a hemisphere. So it's a 3D LiDAR. It's going to look at 180 degrees in front of me. So it's like how an eye works for 180 degrees here. And the color represents how close the object is. So here is the floor, that's the ceiling up there in the dark, this is the horizon, and you have what we have here is this is RGB and corresponding thing. We have clothes here, we have a person here standing right there. We also have some depth cameras. They kind of look like this on the side of the robot. So people's legs or something doesn't go inside. And then how this transfers is, which is a bird's eye view. So you are kind of mapping this, and you're removing the floor and the ceiling here. But this color is a 3D LiDAR, green is a 2D LiDAR, and these are the pointers remembered so far as it's going, and detected the human over here, and that's the typical file. And this is what it's saying, like, hey, these are the obstacles, this is what I remembered. This is a human in this color, this is escalator, you have a different color over here, whatever it's trying to see. So this is just like a very snapshot. Let me try to show you a quick video. So I removed the RGB part in the video, so because I didn't want to expose people's faces. So it will be a little bit tricky to understand what's happening here. Let's see if we have, oh, that's not good. But yeah, here the robot is moving in autonomy. You can see the obstacles are being here. And that's the 3D LiDAR here. So you can see there's some people here. They are detected, they go away. This is a typical perception map here. And people come around, they try to take selfies when it's happening. And the robot has to do its job while not bumping into people. And we have so many edge cases with people trying to book the sensor or video record or whatever it is, but the robot has to still finish its job. However, again, so this is another idea that we want to pursue. We don't have a working example here, but the idea is again that the map that we saw doesn't again have the same high. This doesn't have this high dimensional information in it. We can do this exact same thing that we did on the map, but we can do it on the local map as well. And then you can have this global context coming from your big semantic map, and your perception local cost map is also in the same embedding space. So you can kind of like have like a local context and global context if they use the same family of VLMs. And like this, both global and local context can now go into your path planning algorithm. So it understands that, hey, it's a human, maybe I should maintain a lot more distance from it, or maybe like an escalator, let's not go near an escalator because it's a little bit dangerous, without having to explicitly code all this information. And this is where the other part of the planner comes in. So we try to dabble this a little bit, but without having this local and global context. What we try to do. Oops. Oh, okay. So I don't know if you guys are familiar with diffusion. This is what our motion planning team tried to do, and we're heavily pursuing this idea. Is you can have a diffusion-based path navigation where you have the lidar robot poses and the reference path you're trying to follow, and this is your input, and then you sample a noise, and then you try to given this the cost map or the bird's eye view over there and the RGB image as well, you can try to learn a policy that avoids the obstacle and makes a path around. Now this currently is just taking the LiDAR, the RGB image, the robot poses, the LiDAR and RGB image are passed through ResNet, and just a 1D convolution UNet with a denoised action, and it runs k times to get an action path where the noise converges. This is, I think, the current state of the art. However, I personally believe like this is where I also want to push the boundaries. Oh, sorry. This is where I want to push the boundaries where like it's fine to take RGB image and the cost map where everything just gets to a ResNet, gets to a small dimension. But again, it's losing semantics there. So if we add semantics with the geometrical information on top of it, because we're losing some sort of geometry here, having the geometrical information and a semantic map, this diffusion base would probably do a much better job at this dynamic environments that we see. Certainly an idea that we can and we should pursue because I think this is very hot right now.
With these models, we will be solving on horizon tasks.
Yes.
So let's say you ask the robot, it's in the cashier part, you ask to go coin someplace down the road on the shelf, some number.
Yeah.
But the plan is too long.
Correct.
She's right now this models they're struggling.
Yeah.
So do you have
I do. I think I may have a solution. So let's say you're trying to go somewhere far away. It's hard to make a plan to go far away. But if you know your 3D map, which can be a semantic map, you know where you want to go, that area lights up, and you can have a simple A star or some sort of path plan that jots where the robot is to where you want to go. And then you can run this in the local space. Like as you're moving around, it's in a local space until you go reach there. So that is where like if you don't have the semantic map information and it's telling the VI to do this, it's probably struck. But now you can find that. Thank you. This is the thing in action here. So the green path is the reference path. So we push the robot around. So it's basically the ground truth, which was trained before. And the pink path is the path it estimated using the diffusion policy. So here you can see that, again, this is at the input it goes, it's about the view, and RGB input also goes. And you can see that the pink path is figured out the way around that cart over there. One more time. It's a little bit wonky, but still it's isolating. Where the reference path went straight, because it was trained previously, now you have a dynamic object there, it turned around. But like this is like the diffusion based approach here. Of course, on top of below this, we also have a very traditional algorithm also running, but that sometimes may even fail. I think this is almost the conclusion of our slides, but we also try to just take open VLM models to do manipulation. Most of our products are like, they're like autonomous robots, indoor robots, but we can slap on a manipulation here. So this is like an, again, shelf scanning robot here. I think I may have to do it 2x. Let's do 2x. And now we have trained the manipulator arm over there to grab a certain product that it grabs and puts in the basket there. What you can do here is you can again just go grab me flour. So it knows it needs to go to a certain aisle. It does navigation, and then we might need some sort of okay, you need to be exactly here. Maybe it doesn't encode, but then we can have, okay, you're stationary now, you can go grab it.
So you work with the occlusion, because when you want to pick up stuff on the shelf, they're usually hidden.
Yeah.
So that's the challenge.
It is definitely, yeah. So this is something I think this is not something we completely run, but we know all the challenges exist. So all the known challenges, something we also face, and we didn't necessarily solve them. Occlusions, it's like picking a pack of Doritos where you squish the Doritos, it doesn't make sense, or you drop like a liquid or something. So all those challenges do exist. Maybe there is a way in the future for VLS to figure that out. But yeah, thank you everyone. Thank you for listening. Whoever online as well, thank you for listening. And thank you all for listening. Feel free to reach out to me, and feel free to just reach out to BrainCorp. We do have a few openings. Careers page is there. The openings have descriptions. So feel free to, and if you're even just curious what we do at BrainCorp, please come to our location on site. You can check in, and one of us can just show you all the robots in action, and you can see the lidars and everything. So it'll be nice to host you guys as well someday. Thank you all. Thank you. Thank you. No. Yes.
A question about the visualization.
Yeah.
So you use to take videos of the supermarket, and you know where you is.
We take a video. So when we're trying to localize, yes, we do take the RGB images, and for each and every image, we run the pipeline.
So my question is, will this only work on one supermarket?
In what lab supermarkets?
Oh, when we train the model, I think we use the data from just one supermarket, right?
Yeah, so you can only run that in the supermarket that you get the data on, but you can, I mean, if you're a different supermarket, or a complete different environment, airport or something, you will have to train a map there, which you would obviously need for anything that you want to do, and then you can try to run localizations there. So these two maps, because if they are built from the same family of VLMs, they encode same information, but they will not be geometrically the same. So you cannot run localization here.
Yeah, so when you use the system, what if there are people around the robot?
Yeah, so that's a good question. So this is where I feel like the particle filter a little bit helps, because like the high dimensional embedding vector doesn't necessarily only encode human or the aisle inside. It's also some sort of like higher representation of the whole scenario. So yes, there will be cases where there is a human or things are moved around, but as long as it's like how our human eyes also work, right? Like when we are in like a home goods section, we know, okay, we might be here even though there's some people around. But if we don't know where the checkout aisle is, we kind of like wander around. Oh, it might be on that side. It's kind of similar. On the contrast, let's say if you have shift or odd features, they struggle a lot more, because now it sees a human. It's like trying this RGB space, key point matching. That might struggle a lot more. We did experiment with orb. The same pipeline, we just took orb, we got like 60-65% accuracy as compared to 90.
Thank you. Any questions over the Zoom? On Zoom? Okay. No, thank you again.
Thank you very much. Feel free to reach out if you have any more questions. But thanks a lot. Thank you very much. Thank you. Thank you. My HR.